Well, everybody, Falcha share to this video. In the last one, we finished off on this screen in which the calculations had run, and we had carried out an investigative study on why some of our variables appeared to jump out of the general trend of the variables or the results of the design points on either side of them. Specifically, as we increase the angle of attack of an airfoil for a given Reynolds number, we should have expected to see, if everything was right, that our lift coefficient should have been steadily increasing, our drag coefficient should have been steadily increasing as well, and our pressure coefficient should have been steadily increasing in magnitude. That didn't happen. We had a jump and then it came back down. So we did have kind of a, an out of range value or an out of range design point there. And in checking out what had happened, I'm reasonably confident that it had nothing to do with our method. It had very little to do with convergence. Okay, we're happy that we converged easy on this. And what we did find was that it's more than likely because we're running a steady analysis as opposed to a transient analysis. And that makes perfect sense when you think about it, because we've spoke about it so many times in this series that at a Reynolds number of 50,000, there's a transition. There's transitional points and locations of transition where the laminar flow is developed into a turbulent flow. So by that should give the hint there that if there is a transition, we should be looking at transient behavior, transition, transient. This is a steady state analysis, so we can't expect to capture transient phenomena. So we reckon that's what it is. But anyway, we're now moving on towards the mesh independence study. It is typically, again, something we would have done way earlier, but again, we went down this rabbit hole, and I think I started talking about the design points and what you could do with design points, and then we said, let's vary angle of attack, blah, 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 and then we're off on one. So what we'll do is try to pull this back into line. So what I'm going to do is do this over two videos. This first video is just going to set up for running the grid, the mesh independence study through the grid convergence indexing method. And what I'm going to do first is I'm going to take a copy of this project. I can, if I so liked, could have duplicated this system here, put it, created a new one and ran this mesh into another one. Just show you brave and quick. Let's keep that. I could have took that out. Yes, I could have run this and did say varying AOAs, angles of attack, and that's an assessment there that looks at that, where this one here might have been, say, for mesh independence. Now there's pluses and minuses to doing this. The biggest minus is that I've just doubled up the amount of parameters that I have way over here by putting in the parameters from this duplicated set. Now obviously I'd be taking a lot of them parameters out, but all the same, it's not that worthwhile for me to do that, because I'm also going to be deleting away all the design points. Okay, so that's not what I want to do. So what I'm going to do is, if you just bear with me, what I think I'll do is I'm going to just exit this. Do you want to keep it? No. Okay, I'm going to reopen again because I just want this back to the way I had it. And I'm not going to save as, I'm going to archive that current project and just keep working on the same project. So what I'm doing is taking a snapshot of this project, and I'm going to put it away into a file and then just keep developing. And if I ever want to come back to the snapshot to where I was, I'll just open up the archive file. So if I open this up again, and where I have saved it, and where I've been working out of it, is in the documents folder on my C drive. ANSYS NACA 0009 Workbench project. I exclusively work in OneDrive because I can access my files anywhere. However, when I'm doing CFD analysis, I never save on my OneDrive. I did mention to you earlier that you could look at, for instance, I do this as well. This is done on here, but I don't rely on it. This very thing here at CFD, right clicking onto Fluent, and what we can do let me see if I just get this one up here. Let me see, is it show more options? Where have I this switched off just now at the moment? To keep all the files on the computer. I don't know why that's just not coming up. OneDrive. Normally it would. Give access, combine. Right, I'll check it again later, but generally you can keep a local copy of these files. It may always make available on this device, or there's something very similar to that in the folder that's on OneDrive. Yeah, just because it says it's available on the device doesn't mean it's going to be available when you need it to be available or when ANSYS goes looking for it. However, if it's on the C drive, it's sitting there, okay, and that's what we want to keep. So what I'm going to do on this one here, let me just go Tools or View, and my table has gone. There, it's back again. So it has opened up the way I wanted it. I'm going to go to File and I'm going to archive this. Right. So I'm going to keep the archive file the same, NA25 chord, but what I'll do is add this on for say AOA's angles of attack, so that I'll know that this archive or this kind of snapshot was the angles of attack finished. But this one, what I will do is I'll not put this onto my C drive. I'm going to make this available anywhere I go in the world, and for that reason I'm going to put it into my OneDrive. I go into CFD Fluent. This is a 2D analysis on an external flow, which is an Airfoil. It's an NACA 0009, and I'm going to scoot it into there. There it is. Okay. Imported files external to the project directory. Yeah, I can put that in. I don't have any imported files. That's generally maybe your geometry files, or maybe you had a meshing file that you brought in. We did everything within ANSYS. So I could tick that anyway. It's not going to make any difference as such. However, if you did import a step file or a Fusion file or Inventor or SolidWorks file or that in for your mesh, and you wanted to keep that, yeah, keep that ticked. So we're just going to keep on working onto this one here. All right. So I will rename this one just when I'm at it, and we'll call this one here mesh independence. So these are the 4 steps. In my mesh independence, there's my parameter set. I'm going to do multiple design points, but I'm only going to do 3. So for the grid convergence index method, I'm going to set up a coarse mesh, a medium mesh, and a fine mesh. So my process is as laid out by PJ Roache in 1998, who published an absolutely phenomenal paper on this method, which is this one here. They bring it up in an older one, or 94 was it? There it is there, and he sets out a method, and the other contributors set out a method for working out a GCI, the grid convergence index method. Okay, so the way I've always done these, what I did 3 years ago actually, was I developed a MATLAB script. It was just an M file, the same as I did with the early one that I attached to maybe video 2 or 3. Which worked out the y plus value. I've just last year updated this with MATLAB 2024b, I think it was, when I've started writing my functions in live function now, as opposed to just the M file function. So I have an updated version of that, and that's the one I'm going to run on here. Now, I haven't done an awful lot of testing on it. All right, granted. So hopefully it'll work out okay. So yeah, the calculations that I use in that for the grid convergence index method are laid out by Roache. Celic does have calculations here as well, but for instance, the likes of this phi, which is the medium to fine extrapolated value of that variable, this equation here is slightly different by Roache. All right, it's slightly different by Roache. I will use Roache's, but what I do in my function is I think that one's actually the same as Roache. It's this one here. It's for P, which is the apparent order. It uses a slightly different one. However, I will use the steps that are laid out here. Specifically step 3, step 4, and step 5, bearing in mind that step 1 we've completed already. We've already outputted H in Fluent. We set that up when we set up the design table. So I'm going to use the steps laid out by Selleck here, but I'm going to use the formulas that Roache has put forward. The Richardson extrapolation method there is going to be one of the primary outputs of that, and the formulas are slightly different. But I will again make that MATLAB function available to you. I'll post it into a comment, and yep, feel free to work away on it and develop it as you see fit. Right, so what I'm going to do now is I'm going to set design point 0 to be my current. Why? So I can delete away the rest of these. Don't want any more of these now. Right, delete. That was for angles of attack of 6, 5, 4, 3, and 2. Obviously I have to compare apples for apples here. The only difference that I'm going to do is I'm going to refine my grid from step to step. Now I also have an awful lot of outputs and even input variables here that I'm not going to change at all from grid to grid. For instance, angle of attack is always going to be 0 here for me in this, or always 1, or always 2. But for every grid it's the same. Same with velocity, always the same. So I'm not going to change it, so there's no point having it in the table of design points. I'm going to take that away out. And then there's also output variables here that I care very little about looking at. Now, what I want to take out of this, I'm going to look at 3 variables. I'm going to look at the lift coefficient, I'm going to look at the pressure coefficient, and the drag coefficient. Okay, so the 3 coefficients I'm going to look at. Everything else there I can take away. I will keep y plus on as well, just to validate that as I make a coarser mesh, which I normally wouldn't do. All right, very important to know that. We normally start with the coarsest of meshes, and we get it finer. But just by the way I discretized the domain, the flow domain in a much earlier video, it just happened there that we had landed up with an awful lot of cells. If you recall, we were at 500,000 odd cells, and I took it down to half that was 250, and then I took it down again, where we're now at 165, 600, still an awful lot of cells in there. So what I want to do is I want to let on, or I want to kind of put in case that I hadn't it that well refined, that I had it very poorly refined. I'm starting with, and then I'm going to refine it more. So first what I'm going to do is I'm going to take away the output parameters and the input parameters that I don't care about seeing, and most of them, all of them in fact, are in Fluent. So I'll double click here and I'll open up the solution, and as this opens up, we'll still see our everything potentially might have went back to a lightning bolt now because we deleted away the other design points, or no, it wouldn't have, because we retain the data for design point 0 as well. So we'll still see our discretized domain here in green. That eventually comes up. Okay, this is just going here on the left hand side, down our outline view. At the very bottom, second from the bottom, parameters and customization. I'm going to drop that down. Drop down parameters. There's input and output. Now here I cannot delete input parameters from. Right? If I right click that, it gives me the option to view it. Velocity gives me the option to view it. An input, I can't delete input parameters from there. However, in output parameters, yes, I can. I can delete output parameters. So I'm going to delete the ones that I really don't care about. Now the characteristic cell size, H, I'm going to keep because we want H for our calculation. The drag coefficient, yes, I want to keep that. That's something, one of the variables I'm going to check. The drag force, no. I don't need to see that on my table. Now just because I'm deleting it doesn't mean I'm getting rid of the report definitions. I can still get the plot of that, or the report of that. All I'm doing by taking it away as an output parameter is that I'm taking it out from the design table. L over D, taking that out. Delete L over D. Lift force, taking the force out here as well. Delete. I'll keep the coefficient, I'll keep the Y plus. Pressure coefficient I'll keep, and I'll get rid of Reynolds number. All right, so now what I'm looking at is characteristic cell size, which I'm going to use as part of my procedure in working out the grid convergence index. The drag coefficient is one of the variables I'm going to evaluate. Lift coefficient is another variable I'll evaluate, and pressure coefficient is another one I'm going to evaluate. And then the Y plus is one I'm just going to keep an eye on, so that when I coarsen my mesh up, again, I should have started with the coarse mesh. I don't move to a Y plus value that that's going to cause difficulty for my my turbulence models. So my turbulence model there that I'm running with the SST is the 4-equation one is 1. I have to be in around 1 in order to do that. Okay, so how do you get rid of these input parameters? You don't have to, you can leave all these there, but you're just filtering through more data. And as it happens, the way I take the data off of ANSYS, I usually execute and I solve and I process the data in MATLAB. And the less columns there that you need to extract and filter your way through in an Excel sheet that's exported off the design table, the easier and the faster it gets. Okay, so how do we get away with that? Well, I'm going to come back into named expressions where they were created from, and it'll give me the option there. If I can, let me just see if I can. Sorry, I'm going to double click named expressions, open it here. When you click that, it'll give you an option to delete, but you won't be able to delete it, right? Because obviously it is needed for the cosine of A and the sine of A, so it's used in an expression. You say, well, delete sine of A and cosine of A then, and use A of A. Well, I can't, and I shouldn't do that because I'm using cosine of A and sine of A in a named expression to calculate lift force and lift coefficient and drag force and drag coefficient. Yeah, I can delete the calculation of them variables from my named expression and create a new one just using the kind of native fluent method. Update my reference value on calculate it that way, especially where I'm not varying the angle of attack. Yeah, but other work done. The way I have it there, it's more general. It'll do for any angle of attack without going in. I like it better, so I'm going to keep it that way. But the result of that is that I cannot delete these, which is dead on. But what I can do is when I go to A of A and I click edit, I can untick use as input parameter. So now it's not going to show up in my design table. Okay, so it's still there, but it's just not going to show up in the design table. The other one on that, cell count, is a parameter staying out, input parameter, output parameter, not outputting it from here. Yeah, it's coming from the mesh, apologies, but lost the inlet was the other one. I was right. So again, I need that. So edit, it's going to say the same for this one at 29, uses input parameter, take it away. Okay, and close, and that's it. So I just took off the variables I don't want in order to clean up my table, my design point table. So I'm going to X myself away on out of this one, quit that, and then use the settings for the current and future calculations. Because we've changed how things get reported. Variables get reported, the results get reported. And that's us now. So now when we look into, just say, the parameters here, specifically for Fluent, we're reduced to this, to our Y plus, to our lift coefficient, drag coefficient, our characteristic cell size, H, and our pressure coefficient. That's it. All right, that's in B, in that system, and in this system here, parameters obviously are my spacings of my different sections. Double click that again. There you are. So there's the mesh divisions after the airfoil, and the wall of the airfoil, and the inlet side of the airfoil, and just in the general flow field all around it, our minimum orthogonality and the amount of elements that I have. Grand. And then all together they're lumped here into one big table, and everything there is looking good. Okay. What I'm going to do before I start I'm going to finish up this video now anyway, and then I'm going to go into the next one, which we will wholeheartedly go through the mesh convergence or the mesh independent study through the grid convergence index method. What I'm going to do first though here, just when I'm here, so I can start from like a clean video where I'm starting with a absolutely rough mesh as a starting point. I'm going to roughen the mesh just now. Okay, so I know how I want to refine it. So what I'm going to do is I'm just going to work around here. So let me just see what I have. 220, two 120s and a 180. Let me just try something here. All right, I'm just going to go for, let me see, I'm just going to spacing is equal to, was it 220, two 120s, I think it was, on a 180. Let's double check that there one more time. 220, 120, 120, 180. Okay, I'm going to use an R value here is going to be equal to √2. Okay, that's just what I'm going to use for √2. So what I want to do here is I'm going to make this awful coarse, but I'm going to take this a few steps back. If I made this the fine mesh, I would go 2 steps back to make it coarse, 1 step back for medium, so I go coarse, medium, fine if I was using the fine mesh. But I'm going to maybe take this, I'm going to go 4 steps back just to make it fairly bad. So I'm going to say, let me go for coarse. It's going to be equal to spacing, my spacings, and I'm going to divide that up by r to the power of, I'll just maybe take it back 4 times. And then I'll not semicolon that because I want to read it there. So 55, 30, 30, and 45 is what my spacings would be in that case, which is going to be a phenomenally rough mesh. It's probably unwise to do that because I know one of them is my wall spacing, and I do know that I need to keep a certain amount of, for my turbulence model to be correct, I need to keep a certain amount of spacings along the wall. I think it was the ANSYS, the Fluent Theory Guide, I believe, said between 75 and 100 spacings along the wall. So like that 120 probably would leave it that for this turbulent model I would need to be there, but I know that will also say that's the spacings that you need to get good results. So I don't expect to get good results in the in this mesh. So what I will do, I'll just maybe lessen that slightly, the pain on that. F5 to run, and then we'll run with these. Okay, so I'm going to run with, obviously going to round these to the nearest integer because you can't have, fractions of cells. We have the cell or we don't. So we'll go for 78, 242s, and a 64. So we'll go for, try this here now, 78, 242s, and a 64. 78, 242s, and a 64. 78, 242s, and a 64, just rounding. Okay, and that's it. So I'm going to go with them grid spacing. So as you can see, they're massively, there's huge spacings there. Minimum spacings, huge spaces between, i.e. large cells, and a few of them. Okay, so I'm going to finish this video here. I'm going to hit stop and we'll come back into the next one, and what we'll do is we'll set up, this is going to be our coarse mesh, we're going to set up a medium mesh, and we'll set up a fine mesh from that, the 3 of them. We'll do grid convergent index study on it for mesh independence, see what we look like at the end. Hopefully we'll not be where we want to be, and we'll have to take it a step further. And we'll see how that takes us. Okay, so thanks very much for jumping into the video, and looking forward to the next one.